started. So it's really a pleasure to introduce our colloquium speaker today, Professor Sarah Ballard from the University of Florida. For Professor Ballard got her PhD in astrophysics from Harvard. She then took a Sagan Fellowship to the University of Washington, after which she was awarded both the Torres Fellowship as well as the L'Oreal Women in Science Fellowship, which she took to MIT. And since 2019, she's been a professor at the University of Florida. And Professor Ballard has really a wide range of interests, expertise, impacts in observational exoplanetary science. So she really got her start in the heyday of Kepler, doing a lot of really cool individual system characterization, in a sense, brought into thinking more about population statistics and how we can take this diversity of systems and tie it back to how planets form and evolve. And I'm particularly excited. I really looked up to Sarah since I was an undergrad, and so I'm very excited to hear about what she and her have been working on. So take it away.
That was a lovely introduction. Thank you so much. There's no microphone in this room, right? But folks can hear me in the back if I speak. That is fine. Okay, cool. Thank you. I'm delighted to be here. And before any talk I give, sort of regardless if there's a few exoplanet experts in the room, as I know there are, I like to give some context for why I'm interested in the problems that I'm interested in. And I like to use an analogy that I first heard employed when I was studying. It's an analogy that has to do with the experience of accruing expertise or knowledge in the very human experience. So we start off with the feeling that there's a wide open. And then maybe you take little classes, and right here is bonding groups, like right here is the introduction. We start to understand small areas of things, but the underlying state that connects these ideas is still hidden from you. And hopefully, as time goes on, the water will ideally, maybe you not understand more total material, but you also understand the topology, the things that connect seemingly disparate notions to. So here's where the field of expertise goes. So I'm going to use this analogy to sort of describe how we come to understand the demographics of exoplanets and how they might fit in with other ideas. So as of 2005, it had been 10 years since the detection of an exoplanet around the main sequence star for the first time. Gone by, and we established that at least 1% of Sunlike stars hosted planets. At this period of time, largely the planets that were detected, at least using the transit method, which is the method I'll be focusing on most in this talk, were Jupiters located very close in. So if you were a person in exoplanets, you might be a little pessimistic, potentially, that only 1% of stars appeared to host planets. That's a number I'm going to come back to maybe. In maybe tens of percent of stars hosted planets. We had also detected the atmosphere of a planet as of 2002. The first detection of the atmosphere of an exoplanet was actually the detection of the atomic sodium line. In fact, it wasn't a molecule, but we had demonstrated that it's not only possible to see that planets are there, but also to infer more detailed properties about their atmospheres. We've established that stars of a cross-spectral type host planets. So the eighth exoplanet detected around a main sequence star was detected around an M1. These are stars which are half the mass of the sun and smaller. So even very early in the game of exoplanets, we knew that it wasn't only sun-like stars of those planets. And in addition to that, we were starting to understand what properties might imprint, what properties corresponding to the original stellar nebula from which the star is born might then imprint upon whether the planets form. At the time, it was stellar metal content. Of course, astronomers refer to metal as being anything more protons and nucleus than helium, right? So I'm using metal lightly here. And so here's where we sort of are in 2020. So as a result of a number of missions, including the mission Kepler, which Martin mentioned, we established that there were exoplanets as a function of three axes, right? So not only establishing whether there are hot Jupiters, but the fact that there are exoplanets at a variety of radii, at a variety of orbital periods, and orbiting stars of different masses. So we were starting to fill out this parameter space. This took hundreds of exoplanets to thousands. We had detected not only molecular and atomic species, in the atmospheres of exoplanets, but planets started to detect hazes and dust particles in the atmosphere. In 2008, 2009 were the very first images of planets. So detecting for the very first time photons directly from an exoplanet itself had been happening for about 10 years. And then we were also finding that stellar metal content, presumably the amount to which the primordial disk, which gave rise to both the star and the planets, was formed, affects not only whether planets form, it affects the story of those planets, including their orbital properties. So I'm going to make a guess as to what might be the front page of the New York Times ideas. Actually, I should have looked up what's your most impactful newspaper here. Something Tribune. It's the Toronto Star. Star. So what would it be like the Toronto Star in 2040? And for the New York Times, it's like, are you above the fold, right? Of like the paper. So these would be like the detections, which would be beyond maybe our reach, but potentially just in reach, given where the field of exoplanets, I think, is going. One of those is arguments not just about the existence of rocky planets. If there's any geologists in the room, I'm using plate tectonics loosely. Forgive me for that. So I should say, like, whether there exists evidence for mantle dynamism in rocky planets is something that we'll be very interested in. So not only are there Earth-sized planets, are they like in this particular way? Maybe not the detection of life per se, but the existence of biomarkers, which is to say, are there molecules which are potentially biorelevant in atmospheres? And not only have we detected them around 1 or 2, what is their occurrence? How commonly do they occur? How does stellar activity imprint upon atmospheric chemistry? So we have this story that planets are born, and whatever their star is made of, those planets are made of. Do exoplanets change with time as a function of their star? They do, right? And that's especially true around stars for which the UV flux is sustained over very long periods of time. And we're trying here, it's just small stars in particular. And in fact, maybe this is a huge one, right? The claim of microbial exolife. Some of these things, I think, occurrence rates, for example, are knowable. Microbial exolife is perhaps dependent more on nature, and that might be dependent more on, sort of luck. For lack of a better word, but some of these things can be established regardless. So if those were the big goals in 2040, how might a researcher want to position her research group today in order to understand some of those questions in the future? This motivates why I'm interested in the questions that I'm interested in. I'm going to describe why exactly I've designed my research group the way that I have. So there's a few individual questions that I'm going to focus on. I'm going to list 3 of them here. In my talk, I'm only going to focus on 2. This first one, what is the distribution of orbital eccentricities among planets orbiting small stars? Why exactly I'm focused on small stars, I'll describe in a slide or 2, and why orbital eccentricity should matter so much around the stars is something that I need to focus on. Here on Earth, we are not used to thinking about the tidal heating budget as being a big part of the surface temperature and what dictates the surface temperature on Earth. It's a very small fraction if you compare the amount of tidal heating we receive from the energy from photons from our star. Yet that is not the case for planets orbiting the smallest stars, because they're much less luminous. The planets have to huddle that much closer in to the star to be in the habitable zone, and tidal effects have a really outsized fingerprint on those planets, to the extent that dynamics really play a large role. And then how might system architectures map atmospheric properties? So I'll describe in order to measure the biomarker of atmospheres in a small terrestrial planet, even with James Webb. Let's say that you need 200 hours observations to detect something like ozone. So 200 hours doesn't sound like that much. It sounds like a big ask, but it doesn't sound like that much until you remember that you have to accrue those hours in transit, right? So in order to accrue those hours in transit, you're looking at a baseline of 5 years, potentially more. Is there any way that we can make inferences or even informed guesses about how exoplanetary systems, based on how they're designed, might be included in their atmospheres in some way? It stands to reason because we certainly have simulations of disks that we use to compare to mature planetary systems. Atmospheres must accrue from those same conditions. So is there some way to link these things? Okay, I'm going to talk about these 2 things. One thing I'm not going to talk about today, but I'm very interested in is how dynamically stable are these systems compared to life's evolutionary timescales. Another way of saying it might also be how do exoplanets occur as a function of Milky Way context? I think that's the major direction that the field is moving. There's only so much time and anyone can look with. So maybe ask me about it in the Q&A later, but I think it's incredibly compelling direction. Okay, this is my single favorite figure that resulted from NASA's Kepler mission, which I understand you've had other exoplanet speakers, right, in the past years. Probably had a speaker. Kepler has discovered thousands of exoplanets, right? That's true. This figure is my favorite for reasons I describe. So I'm showing here the x-axis is stellar effective temperature. Of course, stars are burning hydrogen into helium on both ends of this axis. And then you're seeing here on the y-axis the number of planets per star. This original figure of Andrew Howard was interior to 50 days, but it's since been borne out to an AU, a very similar relationship. So the primary science driver of Kepler is deducible from these numbers across the top here. These are showing you the number of stars that went into this calculation in each of these bins. So you can see that for Sunlike stars, which our sun is right about here, the most stars went into this bin. And that's because the primary science driver of Kepler was to establish the frequency of Earth-like planets orbiting Sun-like stars. To call back to that very first slide where I said 1% of Sun-like stars host Jupiters, host hot Jupiters. So these different colors are corresponding to planets of different sizes. Jupiter at 10 times the radius of the Earth would be in order, right? So this 0.01 Jovian planets per Sun-like star is the sum total of what we're really able to achieve from the ground. It took a mission from space in order to see this. These were kind of the lowest of the low-hanging fruit, like all of these delicious planets, right? That were just outside of the reach of precision of what was possible from the ground. There's two things that are suggested. Probably right away you're saying, wow, there's more small planets than large planets. Small at this time being as small as 2 times the radius of the Earth. Since for the Saturn to smaller, even the moons. But more than that, there's more orange than blue. Okay? Is that there's way more small planets around small stars. You can imagine if Kepler were potentially being designed later with this knowledge in mind, you might design the mission slightly differently with the knowledge now that only derived from Kepler. That small planets are so common around small stars. That would move a person in exoplanets from a position of pessimism, of potential pessimism, to a position of extreme optimism, of a feeling of abundance. The reason for that is not only are small stars hosting planets in greatest abundance, they are themselves the most ubiquitous type of star in the universe. So stars half the size of the sun and smaller are 70 to 80% of the stars in our galaxy. They are 0% of the stars you can see with the naked eye. So,
Yeah, sorry to interrupt, but I assume this lines has been corrected for the detectability. Okay, because it's easier to detect the exoplanets, but it's already continuous.
Absolutely, it is. Yeah. So there's an excellent point being made. Isn't it the case that planets are easier to detect transiting around small stars? Wouldn't the same size star produce a deeper transit and a smaller star can do it? Yes. So you have to correct her completeness to make plots like this. That's a whole cottage industry. How to do it correctly. Okay. No, not at all. Oh, they are themselves the most ubiquitous type of star in the Milky Way. Okay. So if you could see them, even the nearest star to Earth, Barnard star, but nearest star to Earth is the sun. Second nearest star to Earth, Barnard star, is an amorph and in fact hosts a planet and it's happening. We know now. We didn't know at this point. We can't see with the naked eye. If you could detect infrared light and you were sensitive to dimmer light, you would see 8 stars appear for every star that you can see right now with your human eye right now. So that means by virtue of being most of the 200 billion stars in the Milky Way, each of them hosting planets, there are hundreds of billions of planets in the Milky Way. That's a result, that was on the front page of newspapers roughly 10 years ago. So having established that dwarfs, and that is stars half the mass of the sun and smaller, host planets, they don't necessarily furnish the conditions for the potential evolution of life that are the conditions that nourished the emergence of life on Earth. So they're different in a number of ways. We're not talking about the same exact circumstances. And the thing I'm going to focus on here is how close in the habitable is. I think it's very useful and it talks about exoplanet dynamics to use this particular framework. We moved as a result of the paper perspective about 10 years ago to thinking about temperatures or in terms of dynamical temperature. This quantity here, we haven't seen it before, and I'm teaching Introduction to Exoplanets for majors this semester. So you probably recall, if you have a planet at a given semi-major axis, its eccentricity dictates the amount of angular momentum it has. Maybe counterintuitively, an angular momentum is maximum when the eccentricity is 0. As you increase the eccentricity of the planet, even at the same semi-major axis, the total angular momentum goes down. So that means this idea, the deficit of the angular momentum, means how far are you removed from the maximum possible angular momentum, which is to say the angular momentum goes by to eccentricity 0. So this is showing a distribution in this quantity, right? So this is actually a theoretical model from this particular paper. So let me introduce you to this idea. We've got eccentricity along this axis, and we've got mutual inclination of planets along this axis. They scale together because of equipartition, another notion that probably sounds familiar from thermodynamics. If you have a low angular momentum deficit, that is, you deviate very little from the maximum possible amount of angular momentum at 0, you're what we would call dynamically cold. Then you have systems up here. High deficit, you would call these dynamically hot. The reason why this matters so much for dwarfs is because even a modest amount of tidal heating is capable of sterilizing the surface of an dwarf because of what would be called a runaway greenhouse effect, right? So even a modest amount of tidal heating, I mean, Io was not a modest amount of tidal heating, right? But thinking about Jupiter to scale with its Jovian moons is actually much more similar to an dwarf scale with its planetary systems than the solar system. It's actually much more analogous to Jupiter and its moons from what we know about Io, constantly being repaid by volcanic activity, right? So like being very close in, having even a modest eccentricity like Io, which is maintained from its resonance, right, from the other moons, means the constant volcanism. Whether or not you could evolve life on a surface like that, who knows? However, if you have a lower eccentricity, you're more sort of inoculated in terms of life. So this is something we would consider extremely relevant, right, to the potential surface conditions on dwarf planets. So how might we establish where planets lie? This is a theoretical prediction from Hubble radiation. I'm showing here a top-down version of Kepler 11. So one of the very first systems that was discovered and published by Kepler, and this is sped up in roughly a factor of 3. First showing top-down and then showing from the side. You can imagine that dynamical temperature should affect the number of transiting planets we detect. So if you have a very flat coplanar system, you're likely to detect more more planets transiting per star. Such a system would light up. Right? So if you see more than one transiting planet, you're likely to see a flatter system, related back to the planets. If those planets have a higher mutual inclination with respect to one another, you're likely to see less planets transiting totally. Such a system would lie over here. Okay, so the extent to which exoplanets are populating this space is something one can constrain with transit statistics. This is what underlies my very first demographic study on dwarfs and their system dynamics. So this was the sum total of the data that I used with the study. This was together with Professor John Johnson. It was a vector with 5 numbers in it. So how many stars host 1 transiting planet, 2 transiting planets, 3? You can see by far most stars host 1, right? You have to be very geometrically lucky to ever see more than 1. We designed the experiment in Bayesian fashion in the following way. If we could carve a stamp of a planetary system, we could change it in 2 ways. One of them would be the number of planets per star. And the second would be where the rate of distribution corresponding to the mutual inclination of their orbits is centered. For comparison, the solar system is 2 degrees on average. We could ask if you took that stamp and stamped it isotropically all over the Kepler field, what would you expect to see? And we established that one model was insufficient to explain this. Now, whether this is a smooth distribution or whether this is 2 populations is something which is being actively discussed in the literature right now. for the sake of an argument, I'll describe this finding as we originally argued, which is that a mixture model is really required. This paper came out in 2016. So this is showing a population of planets which more or less resemble the solar system. Lots of planets, low mutual inclination, right? The solar system light year in comparison with another population of systems where either they're posting less planets per star, or the planets are much more mutually inclined with respect to one another. The discovery of the TRAPPIST system followed soon after this, which is exactly on from this distribution. At the time, we had only detected a maximum of 5 transiting planets around an dwarfs. This was 8. Actually, there's another one after this. The PR figure came out. Extremely flat. So all 8 Earth-sized planets transit this star. So TRAPPIST would lie right around there. Okay, so then to populate dwarfs on this model, population 1 dynamically cold, population 2 dynamically hot. We would say, in order to explain the transiting planet statistics, which is to say the number of systems that would be required in order to reproduce that transiting planet vector, there's about 80% of stars to be dynamically hot, which is to say maybe a little bit more difficult. And you might be wondering, well, why? What would that be? So what produces this population? Is it indeed from population alone? Is there an extent to which planetary systems become more dynamically excited over time? There's really theoretical support for both ideas. And yet it would have really important implications for understanding Ballard potential habitability. So if you were me and we're trying to design a program in dwarfs that established some coherent picture for dwarf dynamics, I contend it should have 3 pieces. And those pieces are all required to support this like one underlying idea. One of them is any coherent picture should be able to explain any one system in detail, right? Including outliers. In addition, that theory should explain constraints of the population level. And finally, ideally, there would be some theory to undergird those observations and those observations that we see. And this is how I've sort of populated my research group. So I'll describe what the students are doing. I'm going to focus on work 2 of them just in this talk. So Sheila working on eccentricities of exoplanets. Chris Lamb, who's working on dynamical timescales, sort of dynamical with demographic information. Padre actually just graduated, so he's soon to be a NASA postdoctoral program fellow at Goddard. He was working on in-body simulations and then affected by energy. And finally, Natalia, whose work is linking orbital dynamics to day and night cycles. I'm going to be focusing on these 2 students in their work. So to get to that very first question, what is the distribution of orbital eccentricities of planets orbiting small stars? What Sheila did in a paper that was published a couple of years ago is to employ a technique which was first employed by Becky and John in 2013. So I'm showing here again a top-down view of a planet. And over here is the silicon eye of Kepler. So given the orbital speed of a planet, the transit should take some amount of time, right? If you have a circular orbit, you know roughly what the transit duration should be. There's some variability depending on exactly where the transit port is, but it should lie within a certain range. If you have an eccentric planet, in contrast, you won't see the transit duration corresponding to an exactly circular orbit. The durations will change. In this configuration, because the observer is looking at parallax, the transit duration will be shorter. In this way, you can carefully build up an eccentricity posterior from many planets. This was something that Vincent Van Eylen did for FGK dwarfs. I'll show that result in just a second. So then it requires some care to take all of these individual eccentricity posteriors and ask, what is the true underlying distribution of nature? One has to take into account the fact that eccentric planets are likely to transit, right? So in order to get out the true underlying distribution of nature, one has to take some care. I'm going to show you the result. So we broke the sample into multi-transit, single transit systems. So as a whole, any individual planet drawn from a multi-transit system has a low eccentricity, maybe that makes sense. Similarly, single transit systems have a higher eccentricity on average. So that looks like we should expect, given how we know visual inclination is vary between these 2 systems. I'm now going to overplot how this looks for FGK dwarfs from Vincent's work. So that's showing these dotted lines right here, meaning Whatever is sloping the eccentricity distribution of small planets orbiting small stars, it seems to be common across spectral time. Namely, less likely to be excited by a jovial companion, which seem to occur much more often around large stars as opposed to small stars. Okay, so given these underlying distributions, and then taking the demographic information that we know, namely 80% of small stars host this kind of planetary system, 20% host this other kind of planetary system, we can describe in a volume limited way what the eccentricity distribution of the planets looks like, orbiting nearby dwarfs. And so that's what she did here. So you can see the contribution of 80% of those sparsely populated systems, even though these dynamically cold systems are only 20% of the population, there's many planets per star, right? So that's what describes this distribution. Again, I'm feeling that these are probably likelier to be experiencing more modest tidal heating. A little bit of tidal heating might be nice. Just arguments there. I'm happy to hear that too. All right, so I debated whether or not to show this next slide. It's the idea really got hotly contested during the archive copy. I'm going to show it anyway, and then because I think it's interesting, the result might look like. So there's one also way in which dwarfs are seemingly extinct, if they are. This is the result that I first saw at Extreme Solar Systems in 2024. Since this paper's come out, the significance of this knot here has gone down. But let me describe, I introduced it to you. So looking at single and multi-transit systems, you can see that eccentricities should be, when projected down, obey some combined distribution, but maybe the average is somewhere around here. What we did not do is break it down as a function of radius. And that's what these authors did. Right? So projecting down in this direction and making the distribution is what was in Sheila's paper and is in Van Allen's paper. This as a function of radius is now showing that there's seemingly an excess of higher eccentricities here. Whether or not this is borne out, I think we'll see a lot later. But I'm going to be much skeptical about it since roughly whatever 11 a.m. This morning. So now I'm going to overplot the intrinsic distribution of radii. So taking into account completion effects and then easier detectability of larger planets. This is showing the underlying distribution of radii in nature. So there's a deficit here, which is often referred to as the radius valley or radius gap. And a seemingly intriguing feature, right, of this paper at that time was that planets in the radius gap seem to be slightly more eccentric. I was interested enough in it to the extent that I had students examine it more. So I had Sheila, who already had all of these eccentricity posteriors for dwarfs, to see whether she saw this. Now she didn't. I had another student pose a slightly different hypothesis, which is if planets of this radius range have a higher eccentricity, potentially it's because of some dynamical event that occurred to elevate that eccentricity. If that's the case, there might be some other way in which these planets deviate from the patterns that we expect or have seen among planetary systems. One of those patterns is called pleasant. It's related to the fact that you resemble your neighbors if you are an exoplanet. So if you take your own radius and you put it in a ratio with the radius of your next closest neighbor, it should peak at around 1. That's what's shown in this parent distribution here. More than would be expected if you randomly drew them. So that sort of resembling your neighbor notion is called pleasant. What we found from radius gap planets, so we sampled just planets which have very precise radius measurements correct within 10%. So we could definitively establish their gap membership. Is that there's a real deficit at 1 at the level of 4.5 sigma. So if you're a radius gap planet, you do not resemble your neighbor. In fact, you look very different from your neighbor. That's interesting. And it's probably to have a look at the radius distribution. So this is now showing the distribution of periods between neighbors, orbital periods. So before this was, what is your physical size in comparison with your neighbor? This is, what is your spacing relative to your neighbor? This overall distribution reflects like transiting planet samples as a whole. You can see an excess right outside your resonance in a couple of very interesting places. Interior to 1.33, generally speaking, it's very harder to be dynamically stable. This is for the parent distribution, and this is for gather planets. And we don't yet really know what to make of it. It's our physical interpretation. Any physical interpretation we go to, which you might be thinking, is it possible to cause this event and the elevated eccentricity from a giant impact of some kind? Such a giant impact would have to strip away the primordial hydrogen helium atmosphere, which it can do. From work from Schlichting's students and others. Then you would not resemble your neighbor who managed to hang on to his or her primordial atmosphere again.
These all efforts are also MGK.
These are only MGK actually. Those were the only ones that we could get like the precise radius. There's some of that from yours also too. So intriguing. This is the first time I've actually talked about this in a program. I'll whether it turns out to be nothing. So let me move on to the notion that I described more in my abstract. And I think now I've established why I think it's so interesting. So there's an assumption that we tend to make about dwarf planets. I mentioned that they're very close in order to be in their habitable zones, right? They almost certainly then would be tidally locked. This is an almost universal assumption in atmospheric modeling, for example, that you have the same side of the planet facing the star at all times. So that is for your permanent day, permanent night. The threats of a permanent day side, a roasting day side, and a freezing night side to habitability are robust. Those threats are intense, including just basic atmospheric stability. Can you move the hot material around the night side quickly enough so that the night side doesn't just condense out into ice? Like, for example, the atmosphere of Io when it moves into Jupiter's shadow, right? So can you even maintain an atmosphere? How might system architectures map to atmospheric properties? So this paper came out, and I understand Sarah visited y'all, and maybe she could talk about this result. Like earlier this semester, I'm so excited by this finding. So before I was interesting, right? Something that I've been very interested in. Sarah made an argument together with Greg Laughlin together about the possible plausibility of an effect. It relates orbital properties together with obliquity. This is the obliquity of the movement, which is to say the seasonal obliquity, right? So Earth's is 23 degrees, give or take. The combination of these two things for a very close-in planet, in order to be in equilibrium, is also related itself to the rotation rate of the planet. So I'm showing here tidal locking. That means like this equilibrium omega corresponding to the planet's rotation is equal to the periodic frequency, the orbital frequency of the planet. So tidal locking corresponds to this line right here. So for most close in, your arbitrary assumption about low eccentricity in dwarfs is that they're tidally locked. Their obliquities are probably low. So that's a very good assumption. What we would think for the dissipation timescale, for the eccentricity of these planets located very close in, for the timescale in which their obliquity should have decayed, right? These are very close in planets. The assumption is that 0, 0, right? And yet Sarah showed that if there was some mechanism by which you could expect the obliquity over long periods of time, and you got to, she invoked such a mechanism, then you could avoid tidal locking. Now, this corresponds to subsynchronous rotation. This idea is not Earthlike in nature. So we're super synchronously rotating. We have many days per year. In this configuration, your day is longer than your year. Okay, so, and yet you would still be experiencing some version of day, which is an important departure from our understanding about atmospheres, if indeed it's happening. The question about whether it's happening is also important because of the contribution of tides. So she was showing here in this paper, based on your obliquity, even if your eccentricity is 0, you'll be experiencing tidal heating from obliquity alone. And that tidal heating could be a substantial component of the total amount of heat your planet is receiving, which is also very different from our canonical understanding of Earth. Energy comes from above, not from below, and dictating your surface temperature, but that might be very different. And so I tasked Natalia with applying to M dwarfs a result from this particular nature paper. So let's return to this Trappist planet. When these authors did a press release on this result, the paper, the figure that nature made for the press result showed these individual planet systems. And actually, one of the authors showed this result in real time using a top and a plate. So you can see, based on the spin precession frequency of the top and the nodal precession frequency of the plate, you can establish a configuration in which you maintain a high obliquity for a long period of time, where you ordinarily would not if just the top was spinning on a plate by itself, right, or in space. So if you have this particular spin orbit resonance, you can maintain an obliquity for a very long amount of time. These frequencies physically corresponding to planets are the nodal precession frequency. This is something which is largely driven by your relationship with your neighbor, right? So like, what is the orbital spacing between planets, the mass ratios between them? Whereas spin precession is more determined by the fundamental properties of an individual planet. Earth's, for example, being 22,000 years. You may have not been. From astronomy 101. So what Sarah showed, which was so intriguing to me, was that sort of using a lot of assumptions, one wouldn't necessarily assume these frequencies are close, but for close-in planets, they are. They tend to be close to commensurability, meaning that this effect might be plausible. I'm not talking right now about capture mechanisms, I can talk about that later. So whether or not you actually end up in a quote-unquote Cassini state, which is the state I'm referring to right now, this particular spin orbit resonance, depends on how you got there, right? So did you actually end up in this exciting Cassini state? Did you end up in Cassini state corresponding to this exciting obliquity over long periods of time? That story is more complicated. The argument I'm trying to make here from this particular paper, restate, I guess, is just that the effect is plausible. So Sarah showed if these frequencies are the same, what would be the obliquities? So she took actually, I don't know if Sam's in the room, she took all the planets that masses measured from the pattern and liquid, right? And she using those masses, she asked some set of known pairs. These are all MGQRs, I think with the exception of two. She asked if these frequencies are the same, what are your obliquity? Now I want you to notice this axis here. So she argued that this effect is relevant. In fact, it could plausibly excite the obliquities of very close-in planets. This is nowhere near around dwarfs, right? So Earth's habitable zone, for example, we look here. However, this is extremely relevant to the habitable zone of dwarfs. And so I asked Natalia to go and recalculate and estimate these frequencies. We have a boost here from M dwarfs because there's more close-in compact systems. Remember, they're only 20% of the total. Yet for FGK dwarfs, they're only 8% of the total. So we have so many closely spaced systems where that nodal precession frequency might be close to the spin precession frequency, corresponding to like a rocky planet, that this in fact we argue is positive. I want you to notice this time scale right here. Recall that alpha for the Earth is 22,000 years. So this is a shorter time scale. Then she's showing here on a very similar scale. What would be the resulting obliquity for these planets? Not all of the time is it relevant to the habitable zone, but there are some planets in the habitable zone of their stars for which this effect is very relevant. Now, if it's actually happening, now that's a big N. I'm going to describe an experiment to sort of test whether it's happening in a moment. That would be a really fundamental assumption that we need to get challenged about how we model and/or atmospheres. So rather than assuming tidal locking, we have a more complicated picture. One of which one's insolation pattern is more varied and dependent on two things. One of them is your seasonal variability. So recall that the tilt is high, including potentially very high, right? So like almost pull on, maybe more extreme than Earth's, which would be right on here. In addition, you're rotating extremely slowly, right? So experiencing some version of day and night. So it's together with a theorist at Purdue who works on oblique planets and understanding ocean circulation that we're running theoretical models. Like what even would we expect? If we don't assume tidal locking anymore, we have to make sure too that we're taking into account not only the complex budget of photons arriving from above, but the heating budget from below. What would we expect? Like I showed earlier, we would expect a non-trivial type of heating. Yes,
Okay, so the left-hand side is the range possible, is the estimate range to.
oh, yeah.
So the right-hand side still is that the problem? Yeah.
Yeah, so we actually calculate, so this is for the whole population as a whole. So then individually, we estimate some distribution for G and some distribution for alpha. We marginalize over whatever those uncertainties are. They're big because we don't know the masses of these dwarf planets. So we're making an assumption for mass radius relation. So based on the relationship between G and alpha, then we go and use the formalism from Sarah's paper to say this would be the obliquity.
I'm surprised about it without consider in the sense that the uncertainties are logical. With this.
You're saying that it makes it possible. Yes, because the uncertainty is so large. Even more, okay, so you would have to have a mass uncertainty, which is larger than one would expect, right? So even given the radius of a planet, you know that the mass doesn't vary in that much. And we know the orbital periods of these things well.
But
Well, these are performance, right?
like the ones on the zeros.
Correct. Yes, these actually are not, it's not possible to excite the ones with the dotted frequency.
But the.
Yeah, the beams, so like the spacing of these planets is close enough that we think we know the normal precession frequency. Now, there is a lot we don't understand about alpha. That is true. So we didn't, yeah. I guess you could make the same argument about the original paper too, right? So they used a set of assumptions. Yeah. So whether or not this is happening too is also based on what was the capture mechanism, right? Like plenty of assumptions here. Let me, now I only have until 3, right?
Yeah, including questions.
Yeah, including questions. So I'm gonna skip this and argue that you saw that precession frequency peaked around 2000 years. So I thought to myself, there's no way to actually see an entire nodal precession of one of these planetary systems. Yet it is possible to measure that precession in theory with changes to the transit duration. So I said before, the transit duration encodes a lot of different information, including the velocity of the planet. It also encodes information about the transit chord. If you're processing, if you have any impact parameter other than 0, and you're processing over time, the transit chord is going to change. So I asked together with Natalia that worked with Prof and Cassini State, who's an expert on Cassini States. We asked if we assume this nodal precession frequency based on the periods that we know. We don't know the longitude of the ascending node at the discovery epoch, so we have to marginalize over that uncertainty. Yet we could ask, what would we predict in terms of how the transit time should change? I'm not talking about an entire period. I'm talking about since the discovery epoch to today. So for Kepler planets, for example, the first transits were observed in 2009. So we have roughly 16 years of time. If in that period of 16 years you've been processing, you might expect some fraction of the time to be able to see a difference. Note that this distribution peaks at 45 seconds, right? So not measurable after 10 years. Yet there is a subset for which at least 90% of the time, either maybe the transit is more grazing, right? Or there's other like favorable configurations that would allow you to actually measure a change in the transit duration. Now, there's many people in the room who I've heard JWST does all kinds of science. One of the focuses of James Webb for exoplanets is atmospheres, to the extent that we measure exquisite transit light curves. The folks who care about atmospheres care about whether those transits vary as a function of color. The thing that they don't care about is the transit duration per se. Yet you could not design a more exquisite instrument that measured the transit duration within seconds. In this sense, it is the case that the most compelling and tasty atmospheric targets, which tend to be those orbiting M dwarfs, for which the size of the signal is larger, the atmospheric size of the signal is larger, they tend to want to look more at multi-planet systems, right? Because you want to do planetary comparison. They also tend to be the systems that we most want to look at. So now I have an exchange student actually from Japan, an undergraduate, who's doing the James Webb data reduction of these atmospheric fits to see whether we see a transit duration, and actually we're limited duration uncertainty at the discovery of it, which tends to be like a few minutes. So whether this is an effect or not, we hope to see. No precession can be driven by a number of different things. But this is something we're sort of looking at. We think we can differentiate potentially between different cases based on what neighbors are doing, whether they're processing all together, for example, or. Okay, so this is sort of. Okay, so I'll conclude with just putting up these questions I think we're compiling in, and I'll take questions.
I guess if you have a multi-planet system, the lower precession G is not exactly just between two planets, right? It's in the whole system. So I guess like.
I'm ready to take it from that.
Right, how would you take it?
Yes, you would have to have a much more expanded formalism than the one that was employed in this like nature paper. We made a lot of different assumptions. So we just employed the formalism in that paper for now. But you're right, it also is difficult to establish would the residence be with your nearest neighbor. Right.
And especially when you see the traffic system set up to certain planets, right? So
Exactly.
you know that we should not expect to.
Yeah, right. Yeah, so like, but I still want to go. Yeah. We already looked at Trappist H, but that one's so far out, we didn't necessarily expect it. Like it would be outside the range of what we would think was captured would actually be what has to happen. Where these two frequencies would overlap. We saw a duration change, but we didn't expect to see one. But you can look at all the Trappist planets and ask, are their durations changing?
Other questions? It's more general question. So you talk about what you are predicting, what would it be
I
for
know.
2040, but I want to know to achieve that, would you kind of like experiment or observations or even theory, like what would it be to achieve this? Do you want more JWST time or more mission like Kepler or high precision radar? So like what will be helpful in terms of like next generation experiment or instrumentation to achieve those predictions 20 years from now?
I actually feel like a lot of most exciting advancements in exoplanets are not observing space at all. They're in laboratories. You know, so I actually think a lot of the most exciting bottlenecks or the most concerning bottlenecks are being explored here on Earth in labs. Let me give you an example. So there's a really important bottleneck related specifically to life and dwarfs, which has to do with UV flux. So a single UV photon can dissociate a DNA, which is why it's so dangerous, right? For like us to receive UV photons. And so there's another particular problem, which is related to forming bio chains of carbons. So life can use molecules that have a few carbons, but it's very difficult to kind of like a primordial soup solvent full of carbons to prevent the process from running away and making it effectively tar, right? Which is not usable by life. So how do you stop that process at only a few carbons? And this result, which was led by a super Ronchen, I think he's a professor at Arizona now, is arguing that some short, whether it's short or long, UV radiation mediated that process and actually allowed you to make those short carbon chains that are necessary for the particular supply. So that was a huge bottleneck unrelated to lower recessions, right? And was instead related to prebiotic chemistry. I honestly think some of the biggest questions are that.
So it's laboratory astrobiology.
I think if you're just asking me, yes.
All right, so we're out of time. Let's thank Sarah again. She will be upstairs for a session.
Yes.